Hello all, welcome to online lecture series on Laplace transforms, lecture number 12. In the last lecture, we derived a property on Laplace transform called division by t, which states that L of f of t by t, that is Laplace transform of f of t by t, is equal to integral s to infinity L of f of t ds. So this property can be extended further as L of f of t by t square is L of f of t by t, so that it can be written as integral s to infinity L of f of t ds 2 times integral of L of f of t. So in today's lecture we apply these properties to derive Laplace transform of some functions. Evaluate Laplace transform of 1 minus cos at by t. So we use the property L of f of t by t, which is equal to integral s to infinity L of f of t ds. In place of f of t, here we have 1 minus cos at. So if we write f of t is equals to 1 minus cos at, then we get Laplace transform of 1 minus cos at by t is equal to integral s to infinity L of 1 minus cos at ds. L of 1 minus cos at can be written as L of 1 minus L of cos at. What is L of 1? It is 1 by s minus L of cos at is s by s square plus a square. So now we have to integrate 1 by s minus s by s square plus a square with respect to s within the limits s to infinity. So integral of log s, before integrating, here in the second term we multiply and divide with 2, so that this term is of the form f dash of s by f of s. If f of s is s square plus a square, its derivative is 2s. So this term is of the form f dash of s by f of s. So that is why we multiplied and divided with 2. So now if we integrate now, integral of 1 by s is log s minus integral of s 2s by s square plus a square is log of s square plus a square, because integral of f dash of x by f of x is log mod f of x. So now if we apply the limits, upper limit is infinity here, but if we apply infinity in this case, we get log infinity minus log infinity, which is undefined quantity. So we first simplify this expression and then we apply the limits. So log a minus log b can be written as log of a by b. In fact, here this 2 log s can be written as log of s square. Log s square minus log of s square plus a square can be written as log of s square by s square plus a square, because log a minus log b is log of a by b. So, and limits are from s to infinity. If we now substitute limit upper limit infinity here also we get log of infinity by infinity, which is again undefined form. So to avoid that, we divide this term s square by s square plus a square, both the numerator and denominator with s square. So that we get 1 by 2 times log of s square by s square. Here in the numerator is 1 by, and in the denominator s square plus a square by s square gives 1 plus a square by s square. Now if we substitute the limits, let us see what do we get. 1 by 2 times log of 1 by 1 plus a square by infinity, that is a by infinity is 0. So that log of 1 by 1 plus 0, which is log 1, and we know that log 1 is 0. Minus and lower limit being s, we just get the same term here. That gives 1 by 2 times log 1 minus, again if we simplify this log of 1 plus a square by s square, taking LCM, we get log of s square by s square plus a square, and we know that this log 1 is 0, therefore this gives minus 1 by 2 times log of s square plus s square by s square plus a square. And to further simplify this minus 1 by 2 can be taken to the power of this term, because m into log a can be written as log of a power m. So taking minus 1 by 2 to the power of s square by s square plus a square, we get log of s square by s square plus a square whole power minus 1 by 2. That is log of s square plus a square by s square whole power 1 by 2. That is log of square root of s square plus a square by s square. Therefore, Laplace transform of 1 minus cos at by t is now equal to log of square root of s square plus a square by s square. Okay. Now let us see what happens when a is equals to 1 in this equation. So if we put a is equals to 1, then we get Laplace transform of 1 minus cos t by t is equals to log of square root of s square plus 1 by s square. So we use this Laplace transform in the next problem. So I want you to note this, that Laplace transform of 1 minus cos t by t is log of square root of s square plus 1 by s square. So now let us move to second problem. Evaluate L of 1 minus cos t by t square. Last problem is L of 1 minus cos t by t. Now it is L of 1 minus cos t by t square here. So let us see how can we solve this. We can write L of 1 minus cos t by t square as L of 1 minus cos t by t by t. Now how does this look like? L of f of t by t. What is f of t in this case? F of t is 1 minus cos t by t. So now let us apply the formula L of f of t by t to this. What is L of f of t by t? Integral s to infinity L of f of t ds. F of t here is 1 minus cos t by t. So this is integral s to infinity L of 1 minus cos t by t ds. And in the previous problem we have already derived L of 1 minus cos t by t as square root log of square root of s square plus 1 by s square. That is integral s to infinity log of s square plus 1 by s square whole power 1 by 2. So now to integrate this log of s square plus 1 by s square whole power 1 by 2, we need to simplify it because direct integration is somewhat difficult. So this power 1 by 2 can be written like this. 1 by 2 times integral s to infinity log of s square plus 1 by s square ds. Again this term log of a by b can be written as log a minus log b. Therefore, this is 1 by 2 times integral is s to infinity log of s square plus 1 minus log of s square ds. Now we will integrate this using integral by parts, and here log of s square is written as 2 times log of s. So now we use integration by parts here, and to get the second term we write this is into 1 here. So now this is of the form integral u into v. So that we can apply by parts, and you know what is integral by parts, that is integral of uv is u into integral v minus integral of u dash into integral v. So in the above integral we take log of s square plus 1 minus 2 log s as u and 1 as v. 1 as v and this term as u. So now if we apply this integral by parts formula for this, we get 1 by 2 times u into integral v, that is log of s square plus 1 minus 2 log s into integral v, that is integral of 1 is s within the limits s to infinity, minus 1 by 2 times integral of u dash, that is derivative of log of s square plus 1 minus 2 log s. Derivative of log of s square plus 1 is 1 by s square plus 1 into s, derivative of s square plus 1 is 2s, minus 2 into derivative of log s is 1 by s into integral v. Integral v is integral of 1, that is integral 1 is s ds. So we applied this integration by parts here, taking this term as u and 1 as v. Okay. Now see, look at the first term. We have limits s to infinity and we have logarithmic terms. If we apply directly the limit, we may yield log infinity minus log infinity, which is undefined. So we first simplify this term. We write 2 log s as log of s square, and we use log a minus log b to write it as log of a by b. And in the second term, here look here, in the second term, if we take the LCM here, we get 2s square minus 2s square minus 2 by s into s square plus 1. So that we get minus 2 by s into s square plus 1. So this is s by 2 times log of s square plus 1 by s square. The limits s to infinity minus 1 by 2 into integral s to infinity minus 2 by s into s square plus 1 into s ds. So here this s, denominator s and the numerator s can be cancelled here. And the first term, log of s square plus 1 by s square, can be written as log of 1 plus 1 by s square within the limits s to infinity. And in the second term, minus and minus becomes plus here. 2 gets cancelled. We remain with 1 by s square plus 1 ds. Now in the first term, if we apply the limit using L'Hospital's rule, we get log 1 as 0. So by substituting the upper limit, we get 0 minus, and lower limit is s. So we get the same term, s by 2 into log of 1 plus 1 by s square, plus, what is integral of 1 by 1 plus s square? It is tan inverse s within the limits s to infinity. So that gives minus s by 2 into log of s square plus 1 by s square, plus, if we substitute the limits, we get tan inverse infinity minus tan inverse of s. And tan inverse infinity is pi by 2 minus tan inverse s. So this is minus s by 2 into log of s square plus 1 by s square plus pi by 2 minus tan inverse s. And we know that tan inverse s plus cot inverse s is pi by 2. Therefore, pi by 2 minus tan inverse s can be written as cot inverse of s. So finally, we get cot inverse s minus s by 2 into log of s square plus 1 by s square, which is Laplace transform of 1 minus cos t by t square. This is very important problem. Just go through it again. If you have any doubts, you can ask me. So let us look into another problem. Evaluate L of e power minus 3t into sin 2t by t. So by looking at e power minus 3t term here, we should get an idea that we have to apply first shift property here. And we have by t here. So we need to apply L of f of t by t property. So we apply two properties of Laplace transform here. First one is first shift property, that is L of e power minus at into f of t is L of f of t with s replaced with s plus a. And the second property is L of f of t by t is integral s to infinity L of f of t ds. We can apply these properties in any order. First you may apply first shift property, then L of f of t by t, or first you may apply L of f of t by t, then first shift property. So consider L of e power minus 3t into sin 2t by t. Now I apply first shift property here. Here we have L of e power at into f of t. L of e power at into f of t is L of f of t with s replaced with s minus a. A is minus 3, so s replaced with s plus 3. And in the inner term is L of sin 2t by t. Now to evaluate L of sin 2t by t, we apply this property L of f of t by t, which is equals to integral s to infinity L of f of t, that is L of sin 2t ds. So first we shall evaluate this internal term completely, and then we replace s with s plus 3. So to evaluate the internal term, we first write what is L of sin 2t. L of sin 2t is 2 by s square plus 4. So we need to integrate 2 by s square plus 4 with respect to s. And integral of 2 by s square plus 4 is tan inverse s by 2, because we apply this formula here. Integral of 1 by x square plus a square dx is 1 by a tan inverse x by a. Here a is 2 here. So 2 and 2 gets cancelled. So we have tan inverse s by 2 within the limits s to infinity, where s should be replaced with s plus 3. Now we apply the limits. Upper limit minus lower limit, that is tan inverse infinity minus tan inverse of s by 2, where s should be replaced with s plus 3. Tan inverse infinity is pi by 2 minus tan inverse s by 2, and pi by 2 minus tan inverse s by 2 is cot inverse s by 2, and if we replace s with s plus 3, in this we get cot inverse of s plus 3 by 2. Therefore, Laplace transform of e power minus 3t into sin 2t by t is cot inverse of s plus 3 by 2. So, we apply two properties here. So, these are practice questions for you. Evaluate L of e power at minus cos 3t by 2, direct application of the property L of f of t by t. And evaluate L of e power at minus e power bt by t. Evaluate L of sin square t by t. You can write sin square t as 1 minus cos 2t by t. So, solve these problems. If you have any doubts, please contact me. Thank you for watching the video. Keep learning.